This video is about the Gram-Schmidt orthogonalization process or algorithm, and we really only have one objective in this short video, and that is to do the Gram-Schmidt process to get an orthogonal set of vectors. The Gram-Schmidt theorem says if we have a linearly independent set of vectors, S, say v1 up to vp, then we can define a new set of vectors t, u1 up to up, where the u's are calculated with this formula. And that new set T will be an orthogonal set of non-zero vectors, and the span of T will be the same as the span of S. If we look at this formula for a minute, we can see that U sub j is equal to V sub j minus this sum where I goes from 1 to j minus 1, and we take the inner product of U sub I with V sub j, divide it by the inner product of U sub I with itself, and multiply all of that times U sub I. Notice that the numerator is going to be a scalar, the denominator is a scalar, so this whole thing is a scalar times U sub I, and we do this for j going from 1 to p. So for each v, we get a corresponding u, and every time we get a new u, we start with the corresponding v and then subtract off this sum. Notice also that we always go from 1 to j minus 1. So when I'm doing, for example, u5, it's going to be v5 minus the sum as I goes from 1 to 4 of these terms. So I'll be subtracting 4 terms here. Some scalar times u1 plus some scalar times u2 up to u5. We can expand this sigma notation like this, which may be a little bit easier to look at. So here's u sub j equal to v sub j minus this scalar multiple of u1 minus the scalar multiple of u2 minus scalar multiple of u3 up to uj minus 1. It's a lot easier if we look at a specific set of vectors. So for example, if I have this set v1, v2, v3 in S, this formula up here would result in these three formulas actually. So notice this one formula is repeated as j goes from 1 to p. So in this case j is 3. So I'll have u1, u2, and u3, three different formulas for each of those. Or really it's the same formula, but each of these formulas is going to have a different number of terms. If I apply this formula to this specific set S, u1 is just v1, u2 is v2 minus this scalar times u1, u3 is v3 minus a scalar times u1 minus another scalar times u2. If I had 4 vectors in the set S, 4 v's, u4 would be v4 minus, well, the inner product of u1 with v4 over the inner product of u1 with itself, all of that times u1, and then minus the inner product of u2 with v4 over the inner product of u2 with itself, all of that times u2, and then I'd have another term minus the inner product of u3 with v4 all over the inner product of u3 with itself times u3. Now of course in this example I don't have a v4, I just have v1, v2, v3, so these are the only 3 equations that I need. But this equation gives you an idea of what would you do if you had 4 vectors in S, or 5 or 6, you just keep adding more terms or subtracting them. Okay, let's do an example with some specific vectors. Here's a set S of 3 vectors in C3, and I'll call them V's, v1, v2, v3, and then I get the first one for free. u1 is just equal to v1, but to get u2, I need to subtract off this term. So I'm going to do the inner product of u1 with v2 here, and then divide by the inner product of u1 with itself. Notice that I just computed u1 in the previous step, and I'm using it in this step. Then when I calculate u3, I'm going to use u1 and u2 that I calculated in the previous 2 steps. So here's v2, and then the inner product of u1 with v2, well, that's just 1 times 0 plus 1 times 1 plus 1 times 1, so 2. And then the inner product of u1 with itself, well, 1 times 1 plus 1 times 1 plus 1 times 1 gives me a 3. And I multiply that times u1, which is here. So I do the arithmetic, and I get minus 2/3, 1/3, 1/3. So there's u2. Then to get u3, I take v3, and I subtract off a scalar multiple of u1, and then another scalar multiple of u2. So here's v3. The inner product of u1 with v3 is 1. The inner product of u1 with itself is 3, as we saw before. The inner product of u2 with v3 is 1/3. The inner product of u2 with itself is 2/3. Here's u2 that we just calculated. Do this arithmetic, and I get 0 minus a half, a half. So if I let T be the set containing these vectors u1, u2, u3, then T is an orthogonal set by the Gram-Schmidt theorem, and the span of T is equal to the span of S. And that's it. So that's how you do the Gram-Schmidt process on a set of vectors to get an orthogonal set.